Let's work on this problem. A block slides down a 150-meter inclined plane as shown in the picture below starting from rest. What is the speed of the block when it reaches the bottom of the incline? So we're going to use conservation of energy to solve this problem. So the initial mechanical energy has to equal the final mechanical energy. The only forces acting on the block are conservative forces like gravity. So mechanical energy is conserved. At point A, the only form of energy that we have is potential energy. And at point B, choosing this as the ground level, there's no potential energy at point B. However, the block will have kinetic energy at point B. So we can set these two equal to each other. As the block slides down, potential energy is being converted to kinetic energy. The potential energy of the block is mgh, and the kinetic energy of the block is 1/2 mv squared. So we could cancel m, therefore we don't need the mass of the block. Now I'm going to multiply both sides by 2. So on the left I have 2gh is equal to 2 times the half. These will cancel, so that's 1. And that's going to equal v squared. Taking the square root of both sides, the final speed is going to be the square root of 2gh. So let's go ahead and plug everything that we have. So it's 2 times the gravitational acceleration of 9.8 times the height of the block, which is 150 meters high. So by the way, this is the height. So that's 150 meters. So if you type this in your calculator, you should get 54.22 meters per second. So without friction, that's how fast this block is going to be moving when it reaches position B. Number 2, an 8-kilogram block compresses a horizontal spring by 2.5 meters beyond its natural length, as shown in the figure below. What is the speed of the block as soon as it's released from the spring? So let's call this position A. And at position B, when it's still on level ground, we want to find the speed as soon as it's released. So at position A, the block spring system has potential energy, elastic potential energy. Energy is stored in the spring. And once it's released, that energy is going to be converted to kinetic energy. Now the height doesn't change, so there's no gravitational potential energy. So we can say the elastic potential energy will be equal to the kinetic energy of the block. Energy is going to be transferred from the spring to the block. The elastic potential energy is 1/2 kx squared. The kinetic energy is 1/2 mv squared. If we multiply both sides by 2, we can get rid of the fraction. So now our goal is to solve for the speed. So we have k, which is 300, and x is the amount the spring is compressed by, which is 2.5 meters. The mass of the block is 8, so let's calculate the final speed. 300 times 2.5 squared is 1875. And if we divide that by 8, that's going to be 234.375. And that's equal to v squared. Now, let's take the square root of both sides. So the speed is going to be 15.31 meters per second. So this is the answer to part A. That's going to be the speed of the block as soon as it's released at position B. Now part B, how high up the hill will the block go? So let's say if it gets up to that height. How can we calculate h? Now at position B, the block has kinetic energy. At position C, where it comes to rest, it's no longer going to have any kinetic energy. The only energy it's going to have is gravitational potential energy. So what we need to do is set the kinetic energy equal to the gravitational potential energy. So this is going to be 1/2 mv squared, and that's going to equal mgh. So once again, we could cancel m. Now let's go ahead and plug in everything that we have. So it's 1/2 times v squared, which is 15.31 squared, and that's equal to g times h. So 15.31 squared times 0.5 divided by 9.8 will give us a height of about 12 meters if you round it to the nearest whole number. So that's how high the block is going to go before it comes to rest. Number 3, a 10 kilogram block slides down a hill that is 200 meters tall, as shown in the figure below, with an initial speed of 12 meters per second. What is the speed of the block when it reaches the bottom of the hill at, let's say, position B? Assuming there's no friction. So at position A, let's call that the original position, the block has potential energy because it's above position B. It has the capability of falling. Now, because the block is in motion, it has kinetic energy. At position B, it's only going to have kinetic energy. So at position A, we have potential energy and kinetic energy. At position B, we only have kinetic energy. So all of the potential energy at position A is going to go to the kinetic energy of the object. The object speed will increase beyond 12 meters per second. So let's go ahead and calculate that speed. So this is going to be mgh plus 1/2 mv initial squared. So the initial speed is 12. We're looking for the final speed. And that's equal to the final kinetic energy of 1/2 mv final squared. So we could divide everything by m and multiply everything by 2. So it's going to be 2gh plus v initial squared, and that's equal to v final squared. So basically, that looks like this equation. V final squared is equal to V initial squared plus 2AD. That's a formula that you've seen in kinematics. So let's calculate the final speed. So V final squared is equal to V initial squared, which is 12 squared, plus 2 times the gravitational acceleration times a height of 200. So it's 12 squared plus 2 times 9.8 times 200, and that's 4,064. And then take the square root of that number, and you should get a final speed of 63.75 meters per second. So this is the speed of the object at position B if there's no friction. Now let's move on to part B. What is the final speed of the block at position B after traveling a total distance of 500 meters, given a coefficient of kinetic friction of 0.21 between the block and a surface? Now I do want to modify this. So let's say that the distance is only for the horizontal portion of the incline. So let's say that distance is 500 meters. So not the total part. So let's say this portion is frictionless, and the 500 meters is only for the horizontal portion of the surface. Knowing that, how can we calculate the final speed of the block if friction only acts on the bottom of the incline? So how can we modify this equation? At position A, we're still going to have potential and kinetic energy. Now, once you add friction to the mix, the final speed will no longer be 63.75. It's going to be less. So some of the energy from the left side is not all going to go into kinetic energy. Some of it is going to go into the work done by friction. Now, if you put the work done by friction on the left side, it's going to be negative W because friction is going to decrease the total energy of the object. And if it's negative W on the left side, then it's positive W on the right side. So this represents the work done by friction. Friction's job is to take away the mechanical energy of the object and to convert it to thermal energy. So the energy lost from the object is going to be W, and that amount of energy is going to be converted to heat energy. So let's go ahead and calculate W first. So the work done by friction is equal to the kinetic frictional force times the distance that the force acts over. Distance and displacement are the same if the object doesn't change direction. So this work is force times displacement. Now the frictional force is equal to mu k times the normal force. So we have the coefficient of kinetic friction, and the normal force on a horizontal surface is mg. Now if this part had friction, that would complicate the problem, because the normal force on, let's say, an incline is mg cosine theta. And this is not a straight incline, so the angle changes, so that's just going to make it more complicated. So let's keep the problem simple. So now let's go ahead and calculate the work done by friction. So it's mu k, which is 0.21, multiplied by the mass of the object, which is 10, times g, times the distance that the object acts over, which is 500 meters. So let's multiply 0.21 by 10, by 9.8, and by 500. So you should get 10,290 joules. So that's the work done by friction. Now let's use that to calculate the final kinetic energy and also the final speed. So the potential energy is mgh, and the kinetic energy at position A is 1/2 mv initial squared, and the final kinetic energy is 1/2 mv final squared, and then plus w. So let's plug in the values that we have. So the potential energy is going to be 10 times 9.8 times a height of 200. And the initial kinetic energy is going to be 1/2 times 10 times the initial speed, which is 12 meters per second. And then that's going to be the final kinetic energy plus the work done by friction, which we could replace that with 10,290 joules. So 10 times 9.8 times 200, that's 19,600 joules. So there's enough potential energy to satisfy the work done by friction, which tells us that the final speed is going to be greater than 12. If this was less than friction, the final speed will be less than 12. Now let's multiply 0.5 by 10 by 12 squared. So the kinetic energy of the object is very low. It's 720. Let me make sure that's right. And yeah, that's it. So now let's add 19,600 plus 720, and let's subtract it by 10,290. So the final kinetic energy is 10,030 joules. So now let's set that equal to 1/2 mv final squared. So we have 1/2 times a mass of 10 times v final squared. So half of 10 is 5, and 10,030 divided by 5 is 2006. So the square of the final speed is 2006. Now let's take the square root of that number. So the final speed is going to be 44.8 meters per second, which was less than the final speed in part A. A 12 kilogram block moving at a speed of 15 meters per second crashes into a wall and comes to a complete stop. How much thermal energy was produced during the collision? So let's draw a picture. So imagine you have a block that's sliding. It's moving at a speed of 15 meters per second, and it's a 12 kilogram mass. And then it collides with a wall. So once it hits the wall, it comes to a stop, so it's no longer moving. Where did all of the kinetic energy go? During collisions, whenever you have an object in motion and then it's no longer in motion, you need to realize that the kinetic energy of that object was transformed into thermal energy. It's lost due to heat. And that heat just radiates outward into the surroundings. Think of, let's say, if you rub your hands quickly, you're going to feel that your hands start to get hot. So all of that kinetic energy that your hands had as it was moving back and forth, a lot of it was converted to thermal energy, and so heat was generated. And that's what's going to happen here. When that block collides with the wall, and both objects, well, the wall's not moving, but the block comes to a stop, all of the kinetic energy that the block had was transferred to thermal energy. So let's calculate the initial kinetic energy of the block. So it's 1/2 mv squared. So that's 1/2 times a mass of 12 kilograms times a speed of 15 meters per second. So half of 12 is 6, and 15 squared is 225. 6 times 225 is 1350. So 1350 joules of kinetic energy was transformed into thermal energy. So that's the answer. Now let's move on to this problem. A 1500 kilogram car moving east at 35 meters per second crashes head-on into another 1800 kilogram car moving west at 30 meters per second, causing both cars to come to a complete stop. So let's turn this into a picture. So this is the 1500 kilogram object. It's a car, but I'm just going to draw a box. And it's moving east at 35 meters per second. And then we have another object, which is 1800 kilograms. And this vehicle is moving west at 30 meters per second. So they collide and they come to a complete stop. So all of the kinetic energies of these two objects that they once had, all of that was converted to thermal energy. So to calculate the total thermal energy produced, we need to calculate the total kinetic energy, which is the kinetic energy of the first object, I'm going to call it object A, plus the kinetic energy of the second object, object B. So let's call this A and B. So this is going to be 1/2 mv squared plus 1/2 mv squared. So the mass of the first object is 1500, and it has a speed of 35 meters per second. The mass of the second object is 1800, and it has a speed of 30 meters per second. So 0.5 times 1500 times 35 squared, that's 918,750 joules. And then 0.5 times 1800 times 30 squared is 810,000 joules. So if we add these two numbers, this will give us 1,728,750 joules. So that's how much thermal energy was produced during this collision. Consider this problem. So we have a roller coaster that's released from rest at point A. How fast is it moving at point B? So how can we find the speed at point B? We need to use conservation of energy. At point A, the roller coaster has potential energy. At point B, all of that potential energy is converted to kinetic. So let's set the potential energy at point A equal to the kinetic energy of the roller coaster at point B. So we have mgh will equal 1/2 mv squared. So we could divide both sides by m. And then if we multiply both sides by 2, we're going to have 2gh is equal to 1/2 times 2 is 1, so it's just going to be v squared. So the velocity is going to be the square root of 2gh. So it's going to be the square root of 2 times 9.8 multiplied by the height, which is 50. So let's go ahead and plug this in. So you should get 31.3 meters per second at point B. So that's how fast the roller coaster is moving at point B if there's no friction in this problem. Now, no friction was mentioned, so we're assuming there's no friction. Now, it looks like I forgot to write part B, so we're going to move on to part C. How high is point C relative to point B? And I forgot to give you the speed at point C. At point C, the speed is 20 meters per second. So with that information, calculate the height of the roller coaster at point C. Point B is ground level. So how high is it at point C? Feel free to pause the video. So I'm going to focus on point A as my initial point. So at point A, all we had to begin with was potential energy. At point C, the object is above ground level, so it has potential energy. Now it's still moving at point C, so it also has kinetic energy. So we need to start with this expression. So we have mgh, this is going to be h initial, is equal to mgh final plus 1/2 mv final squared. Now we could divide every term by m, and so we have this expression. gh is equal to gh final plus 1/2 v final squared. So now let's plug in the numbers. It's going to be 9.8 times the initial height, which is 50, and that's equal to 9.8 times the final height, which is what we're looking for, and then plus 1/2 v final squared. V final at point C is 20. So 9.8 times 50, that's 490, and so that's equal to 9.8 times h, and 20 squared is 400, half of that is 200. Now 490 minus 200 is 290. So let's take 290 and let's divide it by 9.8. So 29.59 is equal to h. So that's how high it is at point C. Now let's move on to part D. How fast is the roller coaster moving at point D? So we're still going to use point A as our initial point. So at point A, we still have initial potential energy. At point D, we still have potential energy because it's above ground level. It has the ability to fall. And at point D, it's still moving, so it has kinetic energy. So we're going to have the same equation. mgh initial is equal to mgh final plus 1/2 mv final squared. And just like before, we could cancel m. So g is 9.8. H initial is still 50. Now h final is now 15. So the difference between part D and part C is that in part D, we're looking for the final speed now. So 9.8 times 50, that's still 490. And that's equal to 9.8 times 15, which is 147. Now let's take 490 and subtract it by 147. So that's going to be 343 is equal to 1/2 v final squared. Now multiply both sides by 2. So 343 times 2 is 686. 1/2 times 2 is 1, so this is equal to the square of the speed. And now let's take the square root of both sides. So the square root of 686 is 26.19 meters per second. So that's how fast the roller coaster is moving at point D. At point C it was moving at 20, and at point B it was like 30 something. So that's how you could solve the roller coaster problem using conservation of energy.